Hello again, everyone. This is a example of a question where we are dealing with the ideal gas law and also the kinetic molecular theory of gases. We're dealing with the definitions of what happens in kinetic molecular theory and the deviations that are associated with that, what sort of things are manifested by the deviations, and an explanation of the observations that we actually have. So the first part, these are mostly theory questions, so a lot of words are going to be involved over here as far as explanation is concerned, but you got to make sure that you're really succinct in sticking to the point of what the kinetic molecular theory actually says. Okay? An ideal gas has a volume of 6 liters and a pressure of 1 atmosphere. When its volume is halved to 3 liters, its pressure doubles to 2. In terms of kinetic molecular theory, explain why the pressure doubles when the volume halves. Assume no change in temperature of the gas. So first of all, in A, whenever we're talking about pressure, pressure is caused by molecular collisions within a container wall. So you have a container like this, and then you're going to have these things hitting the wall of the container. That is what's exerting the pressure. So pressure is caused by molecular, it could be atomic too, depending upon the nature of the gas itself. With the container wall. So we've established what pressure is. Okay? So next thing is that we're halving the volume. So lower volume means that molecules are closer together. Makes sense. Just like people on the dance floor. You have a certain number of people on a dance floor if they're dancing, and then all of a sudden you move the wall, and then the room is only half the size as it was. Obviously, all the occupants are all closer together. So, therefore, more collisions with the container wall. So that means that if the volume is halved, then the number of collisions will double. So that's in terms of kinetic molecular theory. And so V down by 1/2, collisions up by a factor of 2. Okay? And obviously, then this is assuming ideal behavior. So now we're presented with case B, where a sealed rigid container contains a gas at a certain temperature exerting a pressure of 1 atmosphere. The temperature of the container is halved to 150. So you're changing the temperature. It's getting cooler. So obviously when you cool down the temperature, the the molecules slow down. The measured pressure is 0.4 atmospheres. The ideal gas law would predict that having the Kelvin temperature would have the pressure to 0.5. So in this case, the gas is not behaving as an ideal gas. In this example, what property of ideal gases is not true, and why is the measured pressure less than predicted by the ideal gas model? So the things that are not followed at low temperature is that there are no attractive forces. Between molecules. And collisions are elastic. So these are properties that should be followed. These properties are not followed at low T. Well, just think about it. Why is it measured less than ideal? No attractive forces between the molecules. If that's not the case, then that means that there are attractive forces between the molecules. So now the molecules that are supposed to be like this are now like this. So now you have two particles here, you have one particle over here. Obviously, if you decrease the number of particles, you're going to decrease the number of collisions against the wall, because now these two that are sticking together are going to act as one. So therefore, you're going to have less collisions and lower pressure. The other thing, collisions are elastic. Well, if collisions are inelastic, now you have the wall of a container, and then you have this molecule like here that's supposed to be bouncing against the wall and then back out. It's supposed to be behaving just like a regular rubber ball, okay? But now what's happening is that this tends to stick to the outside. So if it does that, then obviously you're not going back and forth, and then this particular molecule doesn't have a chance to go back the other direction in order to form another collision against the wall on the opposite side. So then in that case, the collisions are inelastic. So now you have sort of like a attraction of the molecule to the wall of the container. In other words, it's sticky. It sticks to the wall instead of bouncing off of the wall like it should. So therefore, if you decrease the amount of time this particular molecule is in the air and bouncing back and forth, obviously you're going to have less collisions with the walls. And that's going to lead to lower pressure. So these are the concepts that had to be followed as far as answering this particular problem is concerned. It's a lot of things that you had to consider. You had to remember the definitions and what the kinetic molecular theory really says. What are the certain properties that are associated with them? And to do a little bit of inference as far as, well, what does it mean when you don't have as much pressure? If you don't have as much pressure, you don't have as many collisions. Why don't you have collisions? Because something's not right. It's not elastic. You have smaller numbers of particles. All these things contribute to the pressure itself. So those are the things that you should be considering in order to answer this particular problem.